what we're going to do in this video is we're going to find cosine and sine of 60 degrees and 30 degrees. I'm going to start off with working on 60 degrees for a reason I will tell you later. Okay. So here's a unit circle. Now, all the way around is 360. A fourth of the way around makes a right angle. That's 90 degrees. So if you take 90 and divide that into 3, you're going to get around here is 30 degrees. 30 plus 30 makes 60, so 60 is up here. You can also keep in mind 180 is over here, and a third. Let's see, if you take a third of 180, it's right here. One third of 18 is 6, so we get this. So this is 60 degrees, and what I'm going to do is I'm going to draw a triangle here. And because I'm looking at the unit circle, even though I didn't say, but I'm putting in this context that we're using unit circles. Because it's a unit circle, the radius is 1 and the hypotenuse of this is 1. So what I'm going to do is I am going to, like copy and paste and put this triangle over here like that. Now, just by using the Pythagorean Theorem, I can, if this side here is 1, the hypotenuse is 1, I can find the other two. Well, it's not just the Pythagorean Theorem, it's a little bit more. Okay, so all right, so what I'm going to do here is maybe draw yet another triangle. I am going to draw a equilateral triangle. So an equilateral triangle has all sides that are equal. And I am going to make this a special case where the sides are all equal to 1. And then I'm going to cut this, as I'm showing here, where I draw a line segment from one vertex to the opposite side, and I make it form a right angle. Now, we can go through some geometry that you might have taken class in high school to show that these two triangles are what they call congruent. They have the same shape and size. They both have a right angle, and they both have a 60-degree angle here. Why is this 60? Because when you have an equilateral triangle, you also have the angles all equal. And so the angles have to have a sum of 180 degrees within a triangle. So 60 plus 60, 60 is 180, and they're all equal, so they're all 60. So you have that since this guy is 60 here, that you have 30 over here, and that makes this 30 also. And I'm trying to give the exact geometry theorem here. You have a side, an angle side, a side, angle side. They're all equal, so these two are congruent. Okay, what do we get out of that? That they're congruent. Because they're congruent, these two segments that I'm marking here are equal to each other. And they're equal, and their total length is 1. So therefore, each of these is 1/2. Now, when I go back to this picture up here then, I can fill in some of those things in, and right, especially the 1/2. So here I have 60 degrees, here I have the right angle, this will be 30 degrees, and from what I'm showing here, by taking a equilateral triangle where the sides have length 1, I cut it in half, I get 1/2 and 1/2 for this shorter side. Out of these three sides, 1/2 is the shortest. Now, if I call the other side this altitude, that line segment or that side h, then I can use the Pythagorean theorem to find h. And I get 1/2 quantity squared plus h squared is equal to 1. So that's 1/4 plus h squared is equal to 1. So h squared is 3/4. Then I take the square root, and when I do the square root, I'm not going to do a plus or minus because I'm just looking at sides, and sides will have positive length. So therefore, this is what they call a 30, 60, 90 triangle. I'm sort of just drawing it by, by looking at it. This one's a good one. This one's maybe a little too tall. Maybe it should be a little bit like this. Okay. These are the dimensions of this 30, 60, 90 triangle when the hypotenuse is 1. I should say, because some people might watch this video and say, well, this is not the way I write it. What you can do is you can expand this by just multiplying everything by 2. And if you multiply by 2, the hypotenuse is 2. And 2 times 1/2 will be 1. So that'll make the shorter leg, the shorter side 1, the hypotenuse 2. And then this multiplied by 2 gives rad 3. It's the same triangle, and I like using that sometimes. But anyway, here we're using hypotenuse 1 because we're looking at the unit circle. Okay, so this is a 30, 60, 90 triangle. And the thing is that you can also take that triangle without, I don't see any really big problems with this, and write it like this. Why not? Why? Because we're also interested in the 30-degree angle. So this is also a 30, 60, 90 triangle. You can turn it on its side. And so then, what do we got then? Coming back to, our original plan was to find cosine 30 degrees and sine 30 degrees and cosine 60 degrees and so forth. Okay, so coming back to what we were talking about before, I am going to it's not so good, but anyway, okay, it's not that bad, but it could be better. All right, so this is 60 degrees, and one of the things you sort of have to do is sort of try to remember where that shape is. It maybe could be up a little higher, but anyway, that's all right. So for 60 degrees, we filled this in, that the shorter is 1/2. Let me make it really like more up here. The shorter is 1/2 and the longer is rad 3/2, and then the hypotenuse is 1. So that means I'm going to the right by 1/2. I go up by rad 3/2. So I just slide that 30, 60, 90 triangle, and I think of what does it mean to be the x-coordinate. It means I'm going to the right by 1/2, up by rad 3/2. So therefore, I have now what cosine 60 degrees and sine 60 degrees is. Why do I know that? Because cosine is the x-coordinate, sine is the y-coordinate. But I really believe that part of the key is to see where everything's fitting in. The shape of this, the shape. That's the thing, is I didn't really draw it that well. So I mean, I think it's in some ways it's good enough. But let me see if I do it again or I get it wrong. Okay, but let me just, without doing it again, let me do another one where this is now 30 degrees. So see, here's 30 degrees down here. 60 degrees is up here. And remember, right in the middle is 45 degrees. Okay, now if I put the 30 degree, if I put a right triangle for 30 degrees, it's this same triangle, but it's just moved around. Opposite 30 degrees is the shorter side, because 30 degrees is the smaller angle. The greater angle is 60 degrees, and opposite that is rad 3/2. Okay. So the coordinates then for 30 degrees are rad 3/2. I'm going to the right by rad 3/2, and then up by 1/2. And so this is the cosine, and this is the sine. I believe well, personally, I think that one way some people's memories work is through pictures and shapes. And if you can keep in mind these shapes, you can memorize this and do it in your head of what cosine 30 degrees and sine 30 degrees, if you can fit that shape in like that. Now, the reason these are called special angles is because we can use the Pythagorean theorem to, do some algebra and find these values. There are a bunch of angles that are in between, like say 35 degrees, and some of them you can play around just with these basic ones that we have up here of cosine 60 degrees, cosine 30 degrees, and so forth, and we had the 45 degrees, and using these special angles, you can use those to find others. But some of them you cannot, and like, for example, if you had, I think 37 degrees, I don't think you can find it in terms of square roots, I'm pretty sure. And so we have other ways to do this, which, well, they use calculus, and then those methods are programmed into a computer or calculator, and then you put in 37 degrees in your calculator, press a button, and you can get a decimal approximation. We are working with these 30 degrees, 60 degrees, and 45 degrees because they're good for us to understand. They help us understand math and trigonometry. If we don't memorize these and we don't work with those, say if we just punch things in the calculator, it might be good, it might work out fine, but I don't think you're going to understand trigonometry as well if you do that. So I guess I'm not really imparting new math information. I'm giving my point of view here, little opinion. So, all right. So the idea is that we're going to memorize those values.